At first, there was a boundlessly thick mass of matter. This mass went through an explosion that led to the development of particles, atoms, stars, and cosmic systems that we can observe today. For many years, this has been the explanation presented by physicists. However, later research has presented a new perspective that suggests the universe doesn't have as early a beginning as initially believed. Rather, it could be part of a repetitive cycle in which the universe goes through a progression of cycles of expansion and contraction, possibly in a boundless circle. Brian Cox, a famous physicist, raises doubts about the theory of how things came to be, arguing that something can't emerge from nothing. This questioning adds an intriguing component to the discussion. Moreover, research from the James Webb Telescope has revealed data that contradicts the idea that the Big Bang marked the absolute beginning of the universe. This prompts the key question: if the Big Bang was not the start of the universe, then what was? Join us on this journey to the origins of the universe, where we will explore the frontiers of the Big Bang and answer this question and more. If you are interested in keeping up to date with news about the universe and its surroundings, subscribe to our channel, hit the like button, share this video to reach more people, and turn on the notification bell. Scientists have developed a detailed understanding of the universe in its earliest stages, known as the theory of the Big Bang. According to this model, the universe was much smaller, hotter, and denser than it is today. Roughly 13.8 billion years ago, during that period, all the elements that make up our world were formed in a matter of minutes. In this hypothesis, our universe, including stars and galaxies, was once as tiny as a peach and had a very high temperature of over a quadrillion degrees. Strangely, this surprising account aligns consistently with all current observations. Astronomers have examined everything from the leftover electromagnetic radiation of the early universe to the abundance of the lightest elements and have found that everything agrees with the predictions of the Big Bang. To the best of our knowledge, this depiction fits the reality of our universe perfectly. However, despite its apparent robustness, we know that the theory of the Big Bang is not the complete picture. There's a missing piece of this puzzle, and that piece is an understanding of the first moments of the universe. This challenge is due in large part to the limits of the physical theories we currently use. The combination of general relativity and high-energy particle physics provides us with an important theoretical framework. However, as we delve further into the initial moments of the universe, the mathematical complexity increases significantly, reaching a point where our current methods can't provide meaningful solutions. One sign of this difficulty is the presence of a singularity, a point of infinite density, at the beginning of the Big Bang. This concept suggests that the universe was once compressed into an infinitely small and dense state, which seems illogical. To address this challenge, we need to explore new frontiers in physics, develop an approach that overcomes these limitations, and provides a more complete understanding of the first event of the universe. Our current tools and theoretical frameworks are not sufficiently robust to meet this challenge, so we need to develop new physics that can encompass and explain gravity and the other fundamental forces at extremely high energy. This is precisely where string theory comes into the picture. This theory seeks to be a physical model capable of unifying gravity with the other fundamental forces, particularly at ultra-high energies. Essentially, string theory posits that it can provide an explanation for the first moments of the universe. Within string theory arises the concept of an aeon, which takes its name from the Greek word meaning age or eternity. This idea suggests that the Big Bang, as we know it, was the result of a previous event, implying that it was not necessarily the beginning but perhaps a part of an ongoing process. Extending the concept of an aeonic universe has led to the development of a related theory called cyclic cosmology. Although the idea of a cyclic universe has been considered for centuries, string theory provides a strong mathematical basis for this conception. In the framework of cyclic cosmology, the universe functions as if it eternally oscillates between big bangs and collapses in an endless cycle that extends infinitely into the past and future. This theory of cyclic cosmology was proposed by the prominent physicist Roger Penrose, who was awarded the Nobel Prize. Penrose was fascinated by a remarkable mathematical relationship between the early universe, characterized by extreme density, heat, and smallness during the Big Bang, and the future state of the universe, which is characterized as very cold, expanded, and devoid of matter. The theory suggests that these two states become mathematically identical when pushed to their limits. Although it may seem paradoxical, the total absence of matter could be the driving force behind the creation of all the matter we see in the universe. From this perspective, the Big Bang emerges from what remains almost imperceptibly after all the matter in the universe has been consumed by black holes that eventually disappear into scattered photons in a vast void. The universe arises from what, from another perspective, essentially amounts to nothingness. Although this nothingness is still a form of something that constitutes a physical universe, albeit an empty one, the mystery lies in how the same state can be interpreted as both a cold, void universe and a dense universe, depending on the perspective. The key to this understanding lies in a complex mathematical technique called the conformal transformation, which is a geometric transformation that changes the size of an object while preserving its shape. Roger Penrose demonstrated that the cold, empty state and the hot, dense state can be connected through the scale transformation, aligning their spatiotemporal structures despite their differences in size. However, Penrose argues that the concept of time loses its relevance under these extreme physical conditions. In cyclic cosmology, the sequence of events evolves from an old, cold state to a young, hot state. The presence of the hot, dense state is the result of the previous cold and empty state. However, this causal relationship does not follow the usual pattern in terms of time, as in these extreme states, both size and time lose their ordinary meanings. The cold, void state and the hot, dense state exist on separate timelines, which means that from the perspective of an observer within its own timeline, the cold, empty state would continue indefinitely. Physics and philosophy are intertwined in this realm of cyclic cosmology. It provides theoretical and detailed explanations for the origin of these cycles. However, even if Penrose's ideas gain support in cosmological advances, a deeper philosophical question still lingers about the origin of physical reality itself. How did these cycles come into existence? This leads us to consider the reason for the existence of something rather than nothing, which is one of the fundamental spiritual questions. For our purposes of discussion, we will focus on explanations within the realm of physics, and there are three possible scenarios to consider when exploring the origins of these cycles. First, there may be no ultimate cause at all. Second, there could be an infinite series of cycles where each cycle represents a different universe, and the initial quantum state of each universe is somehow determined by some aspect of the universe that preceded it. Finally, there is the possibility of a single cycle in a repeating universe where the beginning of the cycle is explained by some aspect of its own end. These possibilities are appealing because they avoid the need for uncaused events and provide a more complex explanation within the physical framework. In the realm of physics, Penrose proposes the idea of an eternal succession of cycles, influenced by his interpretation of quantum mechanics. In quantum mechanics, a physical system exists in multiple states simultaneously until it is observed, at which point it randomly collapses into a single state. Penrose suggests that each cycle is influenced by random quantum events that give rise to variations between cycles. This concept opens up promising possibilities for experimental physicists, as it suggests the possibility of detecting subtle traces or anomalies in the leftover radiation of the Big Bang. The quest to understand the origins and nature of the universe has been a central pursuit of human curiosity and scientific inquiry for millennia. From ancient philosophical theories to modern cosmological theories, humanity has continually sought to unravel the mysteries of existence itself. In the context of contemporary astronomy and cosmology, the exploration of cosmic origins has led to profound discoveries and intriguing theoretical frameworks that challenge our fundamental understanding of time, space, and matter. One of the enduring questions that have captivated physicists and cosmologists alike is the nature of the universe before the Big Bang. While the Big Bang theory has provided a compelling explanation for the evolution of the universe from a hot, dense state to its current expansive form, it leaves open the question of what preceded this massive event. If anything, the notion of pre-Big Bang time raises significant philosophical and scientific implications, pushing the boundaries of our knowledge and understanding. Several theoretical paradigms have been proposed to address this question, each offering unique insights and perspectives on the early universe. One such concept is that of the multiverse, which posits the existence of a vast ensemble of universes, each with its own distinct physical properties and fundamental constants. In the multiverse framework, our universe is just one among many, each arising from different initial conditions and governed by its own set of physical laws. The idea of a multiverse arises naturally from certain interpretations of quantum mechanics and cosmological inflation theory. According to inflationary cosmology, the rapid, exponential expansion of spacetime in the early universe may have led to the formation of pocket universes within a larger multiversal landscape. Each pocket universe would have its own unique properties, shaped by random quantum fluctuations during the inflationary epoch. While the multiverse hypothesis remains speculative and difficult to test empirically, it offers a compelling solution to the fine-tuning problem in cosmology: the apparent improbability that the fundamental constants of nature are finely tuned to allow for the existence of complex. Mankind's exploration of the cosmos has been a journey marked by curiosity, discovery, and the relentless pursuit of knowledge. This quest has led to profound insights into the nature of time, space, and matter, and has challenged our understanding of reality itself. Today, scientists and philosophers alike are engaged in a grand endeavor to unravel the mysteries of the universe, from the smallest subatomic particles to the vast expanse of the cosmos. The pursuit of a unified theory that can explain the fundamental forces of nature, including gravity, electromagnetism, and the strong and weak nuclear forces, is at the forefront of modern physics. One of the most promising avenues in this quest is the study of string theory, which posits that the fundamental building blocks of the universe are not particles, but tiny, vibrating strings of energy. String theory offers the tantalizing possibility of a theory of everything, a single, all-encompassing framework that could reconcile the seemingly incompatible theories of quantum mechanics and general relativity. Another exciting development in cosmology is the exploration of dark matter and dark energy, mysterious substances that make up the vast majority of the universe's mass and energy. While dark matter is thought to be responsible for the gravitational forces that hold galaxies together, dark energy is believed to be driving the accelerated expansion of the universe. Cosmological research for decades